Then the last section in this chapter, what we will see is optimization. Optimization problems. The first one is to find the maximum volume. The manufacturer wants to design another box want to design an open box which one side is closed, one side is open, right? To be typically, right, to be clarified. What dimension? Will produce a box with a maximum volume and what is the maximum volume? Right, so an open box having a square face, right? And what we know is the surface area, that is 108 square inches. And what we are seeking is the maximum volume. So that is what we want is the dimension of the box, that how long is the base, how high is the height, and to find out also is the volume. Right, so all the sides are solid, but this one is open on the top. Right, the sides are solid, but the top is open. Right, so let base be x, height be h. Right, that's the starting. Right, we have one base and four sides. Right, the base is x, the height is h. Right, so we have four sides of rectangle and one side of base. Right, the top is open. So the surface area, that's four sides of the side, which the area of the side is a rectangle's area, that's x times h, plus the square of our x. Well, that's the surface area of this box. And the volume of the box is x squared times h. Right, we simply have two variables, but the condition here, right, the additional condition here says that, well, the surface area is 108. It's 108. So still here, right, the volume is a function of x and h. What we're seeking for is to make the volume to be absolute extrema. Right, so we view the volume as a function and we take the derivative of the volume respect to maybe the variable of x. Right, since we have the relationship given x and h, so we can substitute the h out. 108 minus x squared over 4x, which is 108 divided by 4, that's what? 27 minus x over 4. Right, so we get the h to be a function of x, that is 27 over x minus x over 4. Therefore, our volume is able to be x squared times h, that's x squared times, which is 27x minus x to the third over 4. That is our volume. Then to find the largest here, right? So maybe we erase some parts. The box, the height is 27 over x minus x over 4. The volume is 27x minus x to the third over 4. And that is our function. So basically we are finding the absolute maximum based on the volume here, right? And of course we can see that if the box is getting bases to be larger, the height will be smaller, then the volume will be shorter, will be smaller. But if the base is too small, the height is too large, it's also getting as small as the volume. So something in the middle that we get the maximum. Right, so that we get from there. And then to find the relative extrema. Well, how we find the maximum or minimum, which is the optimization here, right? Is finding the derivative of the volume respect to x. That is 27 minus 3 over 4 x squared. Right, and from that, right, so what we have familiar with to find the critical numbers and so on. Critical number is 27 minus 3/4 x squared equal to 0, which this one defines everywhere, so we don't have to let it undefined. That x squared will be 27 over 3 times 6, which is 36. X equals -6 is ruled out since since x can only be positive number, right, we have the base have to be equal to some length, right? Rx equal to 6. Well, we get the critical number. It may or may not be our relative or be our extrema. So we need to use double derivative test. If you want, you could use first derivative, but always a little harder. Right? But the second derivative test, not double, is help us to find out the result. Right? 0, 6 over 4, that's 3/2 x. Evaluate at x equals 6 is negative 3/2 times 6 is negative number. So V volume has a maximum at x equals 6. Right, so dimension, not yet dimension, we need to find out h. H is 27 over 6 minus 6 over 4. That is what? 9/2 minus 3/2, which is 3. Right, so besides any extreme case, well, we get the height to be 3, the maximum where x is 6. That has to be the maximum because that's the only case we have. Right, the function itself is from 0 to 0, it's increase and decrease. Right, that we get 6 to be the relative maximum. Right, which other side, the negative 6 will be a relative minimum anyway. And we see on the second derivative test to verify that we get the relative maximum and have indeed the absolute maximum. 6. So dimension base is 6 inches, height is 3 inches. To get maximum volume, and the maximum volume is x squared times h of x squared times h is 36 times 3 is 108. Cubic inches. Right, dimension we get base is to be 6 inches, which together are 6 and 6, and the height is 3 inches. That if the surface area is 108, that we get the maximum volume to be 108 cubic inches. Right, so not only finding the critical number, but we need to check to see, right, the critical number actually is the extrema we're looking for. And of course, usually we find the absolute extrema, we need to check the endpoints. But usually the optimization question, the endpoints are extreme case, which will make the object to be not exist. Therefore, we're just seeking the relative extrema inside the open interval, which the relative extrema needs or has to be the absolute extrema. So we'll not check the endpoints to be short in this chapter. Finding the minimum area. Right, when we have a paper, right, we usually will not use the entire page to print, right, but we set a margin on top, bottom, on left and right to print it, right, which the page contain 24 square inch of print. Right, the margins at the top and bottom of the page are to be 1.5 inches. To be 1.5 inches, and the margins on the left and right on the top and bottom and the right. The margins on the left and right are to be 1 inch. What should the dimension of the page to be? So that the least amount of paper is used. So we have in this case, a rectangular page, a rectangular whatever a page here, right? In the middle they have printing area of printing area. Also rectangular, it doesn't look like rectangular, but anyway, it should be rectangular as well, right, since its margin is equal. Okay. Right, so we have 24 square inch in the middle. And the margin on the top, on the bottom is 1.5, on the left and right is 1 inch. What should the dimension of the page to be so that the least amount of paper is being used? So the length and the width, right, or the base and the height, doesn't matter what we call it. But to view it, right, we have is, well, the margin on the side to be 1 inch, on the top and bottom is 1.5. Right, and the middle printing area to be 124 inches square. .24 square inch of the print in the middle, and the margins are 1, 1, 1/2, 1/2. Right, so asking for the dimension of the page, but this question looking more easily to set our variable that if we take care of the dimension of the pages, that looks like it's a little easier to do, right? Dimension of the printing area. What we get, let dimension of print be x cross y. Right, the base of the dimension of the print area is x, or the width to be x, the height to be volume, to be y. No, y is volume. And then the paper amount being used, that will be x plus 2 times y plus 3. Now we know that x times y to be 24, and the paper being used is the area of x plus 2. Since x is this length, the paper adds the margin to it. Y is the printing area, the plus 2 margins, that's 1.5 each. And that will be x plus 2 times y plus 3. That we getting from the question. Right, so y will be solving for that, x, y equal 24. If we solve for one of the variable, y to be 24 over x. That's the space, or the area we use is xy plus 3x plus 2y plus 6, where xy is 24, that is 30 plus 3x plus 2 times 24 of x, 3x 48 over x plus 30. Right, that is our S, which is the amount of paper, basically, right? Area of the paper. Then we are getting the function of x can be represented by to the area using that we're just finding the derivative. That is 3 minus 48 over x squared. My first derivative, right? That's x to negative 1 times x to negative 2, which is that. And this one, x cannot be 0, of course, has to be positive. We let that equal to 0 to find the critical number. X has to be 4 for the x, right? 4 to get the critical number. Maybe a little too fast, right? So to find the critical number, we need to let ds dx to be 0. That's 3 minus 48 over x squared equal to 0. X squared has to be 16. The x to be 6, or x to be 4. Negative 4 is ruled out. Right, I'll find is the critical number. We have x to be 4. I will save some information over there. xy is 24. The s is and the ds dx, that is 3 minus 48 over x. Critical number possibly at x equals 4. Then from the information we get, right, at x equals 4, we need to verify this one is the least amount, right? So verify it is actually the least amount. We need to find the second derivative. That's negative 48 times negative 1 times x to negative 2. That's 48 over x squared. It's always positive for all x. Right, therefore, x equals 4. Yields a minimum area. Right? Because we have the second derivative is always positive. So at critical number, it's always the least amount of paper using. Right, so the dimension of paper, that's the width right, the width or the length we call it in the rectangular, right, length and width to be x plus 2, that is 6 inches, and the width to be y plus 3, which is the y we don't know yet, right? X to be 4, y is 24 over 4, that is 6 inches. So 6 plus 3 to be 9 inches. Right, something I forgot, so put it on the side, right? It's also fine. X equals 4 yields the minimum area, in this case y equals 6. Right, that we get the length to be x plus 2, that is 6 inches, the width to be 9 inches. Right, they didn't ask us to find the minimum usage of the paper. If they ask, we say, well, that 6 times 9 is 54 square inches. Right, so that will yield the minimum use. So the idea, if we can able to graph the object of what they described, then try to graph them, and maybe we'll have a better view of what we're supposed to do, right, in the middle. Then just simply to make the function, if that's multivariable, into single variable expression, then we are able to take the derivative of a function and find out the critical number, verify that we need the extrema is what it is at the critical number, then to continue with the question. And for something not able to graph, then whatever it is. Like the next one, finding the maximum revenue. Right, the demand functions. Right, the demand function of a product is modeled by this function p equal 56 times e to the negative 0.000012 x. What p is the price. Price per unit. And x is the number of units what price will yield a maximum revenue. Right, the revenue is just the money you got from sale, which the revenue will be the price, the unit price in this case, times how many units it's being sold. Right, and to be clearly that it is intuitively that when the price is getting higher, the demand will getting lower usually. Right? That we have the revenue is to find the maximum revenue. Right? The revenue will be price times x. That is x times e to the negative. That is price or we rewrite a little bit, 56x e to the negative 0.000012x. Right, so that is the revenue. So to yield the maximum revenue, we need to find the derivative. Right, that is the function of x in this case, which we have the derivative, right, u prime times v plus v prime times u. Right, that's so many decimals we have. Then 56 that's negative 0.000672 0.000672 x. Right, that's our first derivative. Right, to be this thing, we get 56 minus e to the negative 0.000672x minus e to the negative 0.000012x. Right, to find the critical number, we have the derivative of the revenue equal to 0. That this exponential function can never be 0, which is just this part. when we divide, it's about 83,333. Decimal point, we don't count it since that is the unit of the object. A critical number, it has to be 0.33 anyway. That is 25,000 divided by 3. Right, anyhow, that is our critical number. So maybe I can erase that part. And the critical number is at x equals 25,000 over 3. Well, that's the amount of unit it will get. Then we find the second derivative. That is negative 0.000672 times e to negative 0.000012x u prime times v minus v prime plus v prime times u. That maybe factor out the negative 0.000012. E to the minus 0.000012x. We get 56 plus 56 minus 0.000672x. And we get 25,000 over 3 as dx, that which is the result is 56. Then we get x to be 25,000 over 3. That here's a negative number times a positive number times a positive number, which is smaller than 0 as concave down. So x equals that one. To 150,000 actually. Yields the maximum revenue. It yields the maximum revenue to verify using the second derivative test. We show that, well, this value will get a maximum revenue. And regardless what is the realistic case, right? The price in this case is e to the negative 56, e to the negative 0.000012x. $50,000 divided by 3. Which we got a negative 1 over here. That is about 56 over e. Right, so we get the price to be $20.60. So the price of $20.60 yields the maximum revenue. So this question is a little more trickier. I will get the price unit to be that, and of course in real case the unit will be a little, maybe the 3, maybe 83,333 or 83,334. That's our unit to be. But as we set the price, we just set the price into it and to see what unit it will give us. Right? Doesn't matter what it is. But just regardless in the real case, right? For real, we need to make the units to be a whole number. Then we are able to find out the price to see which one will get the maximum revenue. Right. So that is the optimization question. We just analyze, nothing else but just analyze the question to find the relationship of a function, what we have, and what they're asking, and then to set up the find the derivative critical numbers and verify the critical is the extreme we're looking for, and finally find out what the question is asking. Right, so that is section 4.7, right, which is the second part of our course all the way, right, to wrap up everything. Then next we're going through something different. So thanks for watching, and I'll see you next time.